Hey kids, we're going to look at improper integrals today, and those are going to be integrals that have the infinity sign located in them somewhere. So we've got three different situations that could happen. One, we could start at a specific number, call it a, and if we start at that specific number a, we're going to let our integral go to infinity. So we're going to start at a specific place, stop at infinity. And what this means is, instead of working with solving out the integral of the function, we allow b approaching infinity, and we look at the integral from a to b of f of x dx. So maybe sometimes when we look at those limits with the integrals, sometimes we can identify things a little bit easier. Okay. The second part is the same thing, except now we're going to start at negative infinity and stop at some point b. And again, we're going to allow a to go to negative infinity, and we're going to look at an integral and find the limit of that integral. And then part C is if we go from negative infinity to positive infinity. So there's no breaking point. And what we have to do then is combine the first two integrals, and then once we split this negative infinity to positive infinity, we'll go from negative infinity to some point C. We'll go from some point C to positive infinity. So we're going to add those two integrals together. That gets us our original integral. And then what we can do is we go, hey, this guy looks like part 2. This guy looks like part 1. And so basically, anytime you have an integral where you go from negative infinity to positive infinity, you're looking at a situation where you have two small problems inside of it. Okay? These are improper because there's not a specific start or stop point on some of these integrals. Remember, when we look at a definite integral, you typically have a starting value and a stopping value. Well, infinity can't really be claimed as a specific value anywhere. So what we've got is an improper integral. Okay, let's take a look at how this is going to work. Okay, so let's look at a problem now where we can try this. And of course, let's do from negative infinity to positive infinity right off the bat. What we need to do then is we need to break this up, and we need to pick some value c that we're going to stop at to get our constant. And 0 is always ideal to do this with. You can use any number you want. I like to choose 0 because when you integrate with a 0 in there, there tends to not be a lot of problems. So here's our setup. From negative infinity to 0 of e to the x dx plus 0 to infinity of e to the x dx. What this allows us to do then is look at those first two situations that we had. And so I'm going to replace negative infinity with b. I'm going to let b go to negative infinity, and I'm going to look at the integral then from b to 0 of e to the x dx plus, and then I'm going to look at the first guy, which is the limit as a approaches infinity from 0 to infinity of e to the x dx. Whoops, that shouldn't be 0 to infinity. That should be 0 to a. All right. Now, when we try and solve these guys out, what we've got is a situation that we've got some different things going on. So I don't know exactly how this pink limit works out, but what I do know is that when I integrate e to the x, I'm basically looking at the integral of e to the x evaluated from b to 0. Okay, and it's stop minus start, so that's e to the 0 minus e to the b. Okay, anything to the 0 power is 1, so this first guy becomes 1 to the minus e to the b. Okay, not too tricky there. Do the same thing over here with the next limit. So we're going to, again, integrate e to the x, which is e to the x, and we're going to evaluate it from 0 to a. Well, it's start minus stop. So this is going to be e to the a minus e to the 0, which is going to be e to the a minus 1. So when I look at these two limits, my pink limit, what I'm going to end up with here is, in pink, I'm going to have the limit as b goes to negative infinity of 1 minus e to the b, okay, plus, and then in the green color now, I'm going to have that limit as a goes to positive infinity of e to the a minus 1. Okay, now we can actually substitute the infinities into this. And when I do that, what happens is 1 stays the same. It's just 1. But negative infinity in here for e is going to give us a very, very small number. So this is going to become 1 minus 0. Plus, and then on the other side, as I put infinity in for a, that's going to be a very large number because it's going to be e to some huge ginormous power. So that's going to be infinity minus 1. So when I look at this, I'm going to wind up with a situation where I have infinity as my answer. Not approximately, but this is going to equal infinity. So the question then is evaluate that integral and state whether it converges or diverges. Well, an integral converges if it approaches or meets or reaches one specific number. It diverges if the integral doesn't approach anything at all. And in this case, as we go towards infinity, our integral would be divergent. So the three dots mean it diverges. Okay, so that's how this guy's going to work out. It's not too bad at all. These are steps that we can do for everything. So basically, and let me just make one small change here. Infinity minus 1 is still infinity. So what we wind up with, for a point of clarification, is right here I get 1 plus infinity as my limit. So that this would also be 1 plus infinity. Sorry I didn't catch that right off the bat. All right, so there's the first example. Not too bad, but it's different. Okay, it's back to now evaluating indefinite integrals. So we have to remember the whole stop minus start situation. Well, let's look at the next guy. We're going from 1 to infinity of dx over x. Okay, remember this is the same thing as going 1 to infinity of 1 over x times dx. Okay, so what we want to do is we want to look at the limit then and take infinity out. So the limit as a approaches infinity of the integral from 1 to a of 1 over x dx. And if we integrate this integrates, the 1 over x integrates to natural log. So this becomes the limit as a approaches infinity of the natural log of x evaluated from 1 to a. So when you do that, it's stop minus start. It's going to be the natural log of a minus the natural log of 1. And the natural log of 1 is 0. Okay, so we're going to have the limit as a approaches infinity of the natural log of a. And this guy also approaches infinity. So since he approaches infinity, we would also say that this guy diverges. So there you go. There's your introduction into improper integrals, and we're going to work a lot more of these because they can be a little bit tricky.